So let me kind of give you a preface to what the talks will be about, and then I'll dive in with the first talk. And the real idea that I want to get across is that Gibbs measures of certain flavors end up being very valuable in the analysis of some non-equilibrium, non-reversible probabilistic systems that occur in the context of integrable probability. And many of these words will require some definition or some meaning, but just to kind of get you thinking, you see a lot of Gibbs measures in things like statistical physics, the Ising model, the Potts model, the hardcore model, things like this, and you see dynamics, Markovian dynamics, for which these are stationary, but these are usually because they satisfy detailed balance, right? There's some reversibility. So you have like Glauber dynamics or things of that sort. And so you're almost building the dynamics so that you have these nice stationary measures. But in the world of things like interacting particle systems, you have other instances where you have something like, say, product measure on the line, and you run something like the exclusion process, and this is generally a non-reversible process, but you still have product measures invariant. The product measure is a very simple example of a Gibbs measure, and this is an instance of a Gibbs measure being invariant under a non-reversible dynamic. So what I'll talk about will kind of generalize away from that. We'll be studying different Markovian dynamics for which kind of more general, more complicated Gibbs measures end up being stationary. And oftentimes these Gibbs measures also give us a way to analyze the processes themselves. Okay, so we'll delve into so let me tell you kind of what we'll do in the lectures now that I've kind of given you this overview. So in the first two lectures, I'll talk about a very kind of concrete and everything hopefully will be concrete, but a very concrete example where this principle goes forward, which is the analysis of last passage percolation, which is a very simple model, in a strip. And what we'll see there is that the stationary measures for this process can be characterized in terms of what I'll call a two-layer Gibbs measure. So it's a Gibbs measure that's supported, in a sense, on a two-layer graph, and the marginal on the top layer ends up being actually the stationary measure. So this is going to be a generalization, I'll explain how, of the first thing I said, which is that product invariant measure is often stationary for things like exclusion processes. So this will generalize this, and I'll explain the result in the first lecture, really, and then the proof in the second lecture. And what we'll get a flavor of in the second lecture is that the proof relies on certain kind of algebraic properties, things called Cauchy and Littlewood identities, but very, very simple versions of these. In the third lecture, I'm going to kind of take this perspective that we'll introduce in the first two lectures of these two-layer Gibbs measures, and I'll build more layers. I'll introduce a slightly more complicated setting, which will relate to something called Schur processes. Okay, the Schur being related to Schur symmetric polynomials. And I'll describe how the same sort of principles and ideas that give the stationarity of the processes that we'll talk about in this first lecture give rise to nice two-dimensional Markovian dynamics that these Schur processes are describing and tools to analyze that. So really in the fourth and fifth lecture, I'll analyze the properties of Schur processes and the probabilistic models that go along with that. I'll introduce ideas of determinantal point processes, determinantal coming from the determinantal structure of Schur polynomials, and then also how you can leverage the Gibbs property that these objects are defined by in order to extract asymptotics. So that'll be the fifth lecture. The final three lectures will be really focused on kind of understanding where these Gibbs measures that are going to be kind of batting around in the first few lectures come from. And so I'll talk in one lecture about the RSK correspondence and kind of give a different perspective, if you've ever seen it, than you probably have seen. And then the final two lectures, I'll talk about what's called the Yang-Baxter equation, which is kind of a kernel through which you can then extract all sorts of nice probabilistic information, including these Gibbs measures and Gibbs properties for a whole host of different systems. Okay, so the lectures will kind of balance between probabilistic and integrable, and well, that was explained in the name of the lecture series. There are a number of exercises that are kind of scattered throughout, and there are also a number of mistakes that are scattered throughout the lecture notes. You'll probably have an easier time finding the mistakes than solving the exercises, but I found my first mistake in the first lecture, so I'll point that out. Okay, so let's jump in. So the structure of this first lecture is that I'm going to start by introducing. I'm not as tall, so I won't get as much information on the board. I'm going to start talking actually about what's called geometric last passage percolation, and I'm going to introduce the model actually on the whole plane on Z2. Okay. This is not what I'll focus on, but it's good to kind of introduce the ideas, and then we'll talk about stationarity or stationary measures for this model. And then I'll introduce the model in the geometry that I'm actually more interested in, which is in a strip, and talk about the stationary measures and results about that. So you should imagine you have a lattice, Z2, and at every lattice point you have a weight, a random variable, Wij. Let me know if at any point my handwriting gets too small. I'll try not to venture in that direction. And theseWij's are distributed as geometric random variables with some parameter q, where I'll assume that q is, well, between 0 and 1. Okay. Just because one should define objects when you first introduce them, the probability distribution for this is geometric that's supported on z bigger than or equal to 0. So in other words, if I have a k, which is in that set, the probability that I equal that is, well, it's whatever I wrote in the notes, 1 minus q, q to the k, so for k in this set. Okay. Now, so I'm going to have these, but these are going to be IID for each ij in Z2. Okay, so I have all of these weights. You can think of them as, amounts of money at each site, or waiting times associated to each site, or whatever you want. Now, between any 2 points in the plane, so maybe P and P prime, there's a notion of a partially ordered set, which just says that P is less than or equal to P prime if that's true in each coordinate, right? So obviously points where one coordinate is bigger and one coordinate is smaller, like this point and this point, there's no comparison, but these 2 points are obviously ordered. Okay. So for any 2 such points, I can define the last passage time, G, P, P prime, and this is some sort of, well, it's almost like a negative metric or reverse metric, which is defined as the maximum over paths. I'll use pi to denote paths, P to P prime, and I'll tell you what type of paths in a moment, of the sum over all ij in the path of Wij. So by a path, and let me try to illuminate this with some color, a path will always correspond to, will always mean pi is an upright lattice path. Okay, so upright lattice path means that it moves between lattice points, and it only moves either to the right or up by unit 1 increments. So probably I should try to go through the origin if I want to do this right. All right, so let's say P was down here. Sorry, okay. And ij in pi is the set of all points in pi, but this excluding the starting point. I could have included it, but for a purpose in a moment, it's just helpful not to include it, because I'm going to kind of now talk about boundaries, and I want to have some initial data on a boundary. Okay, so this is the picture. So this would be one instance of pi. Now, of course, you see there are many choices of pi, and for each choice, you take the sum of the weights along that path, and now you maximize over all things. So on a given path, the weights that you encounter are independent, but when you start to take the max over lots of paths, then there's dependence between each of the terms you take the maximum of, and hence this random variable is somehow a non-trivial object. It's not just the sum of IIDs, because it's the max of correlated sums of IIDs. Okay, is the definition of the object clear? Okay, so this is sometimes called the last passage time. For a reason that I'll make clear in just a little while when I give a more geometric interpretation of this. Okay, so, and let me just say that you guys should feel totally free to interrupt me with questions along the way. I have. So this is the point-to-point last passage time, but it also makes sense to talk about last passage time. Maybe I'll erase this from a boundary where I specify some sort of initial data. So for instance, let me imagine taking, and I'll use yet another color. Imagine that I have some sort of infinite path. Maybe it kind of zigzags along. All paths should be lattice paths, even though obviously I'm not drawing it very well. So a path like this I'm going to call gamma. And gamma is what's going to be called a downright path. Okay. That just means it's a path that goes infinitely in both directions, and if you kind of follow it from this side, it only takes steps to the right or down. So, simple examples of downright paths you could have in mind. Well, the boundary of the first coordinate of the first quadrant is a downright path. It just goes down and then it just goes right. The x-axis or the y-axis are both downright paths. Or something like this, which is like a zigzag path that kind of goes at slope -1, is a downright path. For that matter, like any sort of random walk type trajectory, which is just down and right, word. Okay, so for any downright path, and let me call the dr is the set of all downright paths. Okay. For any downright path, let me define an object which is called the k-shift of it. So this is just equal to the set of all points plus kk. Okay. I don't know how to write that well, but anyway, this is just, if let's say k is equal to 1, this just means shift every point to the right by 1, in both coordinates. So the new path will just be this sort of shifted version, if I could draw it well. Okay. Good. Now for a given downright path, so given a downright path, so let G naught of P for P in the downright path be a set of random variables. They could be arbitrary, they could be constant, they could be IID, whatever you want. And given that initial data, so we'll call this initial data, along gamma. And now we can define the last passage time relative to that initial data. So for any p prime, Okay, so for p prime, which is anywhere to the kind of upright of gamma, so I can write that as in gamma to the positive shift, bigger than or equal to shift. I can define a passage time from this boundary condition into the bulk as the max overall paths from, let me write it like this, over max over all points where you can leave the boundary of the initial data. Plus the passage time from that point into the bulk, to pp. So the picture you should have in mind is you've specified some initial data on gamma. So maybe at each one of these points we put some numbers. Maybe I put the number 4 on this point, and actually you see the value on these sort of inner corners really won't matter, because you can never really get to this without first leaving one of these points. But anyway, so we have some numbers, -2, -1, so on and so forth. And what I now look at is overall paths that maybe I need to specify. Okay. Anyway, so I look over all paths pi that start at some point along gamma and then kind of leave gamma and go up to p prime, and I try to maximize over the starting point and the bulk contribution. So there are two different effects. There's whatever the initial data is, and then there's the effect of the inner bulk. Okay. Now let me just kind of tell you in words what type of stuff one might hope to see from this model, and then I'll tell you some results. So this is a variational problem where you have some initial data, and then you have some maybe random initial data, and then you have some random evolution of that initial data that's given by these inner weights. And so a very natural question is, well, what happens if your initial gamma converges to something? You zoom out and converges, let's say, to a straight line or some curve, and your initial data, this g naught, converges to something. What will happen to this gp prime? So if I take p prime to be like n times x times n times y, I take it really, really far off in this direction, I can ask, is there a law of large numbers for that passage time? And what does it look like? Yep.
Could you explain again why is the values there are not useful?
Oh, yeah. OK. So I should probably specify that. OK, you can define it where they are. But so there's a little bit of ambiguity, I would say, in my definition here. But maybe I want to say something like the external points of this. So basically, what I want to say is that if you depart here, you're going to be forced to encounter another point along gamma. And what I really want to think of is that I choose one point along gamma and then only use points inside of the bulk. And so if I restrict myself to that type of path, then I'm forced to kind of not use these inner corners. Okay? Anyway, somehow this is maybe not so important, but yeah, so maybe I want to restrict myself a little bit. But yeah, so the question is exactly this sort of thing, like what is the law of large numbers as I move deep into the bulk? How does the randomness of these geometrics impact it? Is it just that is it the same as if I replace the geometrics by their mean? Would I get the same answer? And the answer is no. It's not, I can't just imagine solving this variational problem with deterministic, q as the variables. The randomness matters. And a completely open question is what if I replace the geometrics with arbitrary random variables? What will the law of large numbers be? Now, you can give some characterization. You can prove that there is a law of large numbers, but actually computing it is not something that you can do. So what is kind of the direction of interest is exact calculation. So how do we compute the law of large numbers? We put we go very far out. We go nx and ny as these coordinates. What does it converge to? What is the formula for it? And in order to get in that direction, then of course there's questions of fluctuations, and we'll go into. But in order to get into that direction, it will be very helpful to understand stationary measures for this model. And we'll see that because of the special properties of geometrics, the stationary measures are very, very simple and easy to access. Okay, so that's the direction we're going to aim in. But let me kind of finish with the introduction of the model with just one more bit of information, which is so I've defined this. Let me kind of talk about a special case that people are often interested in, which is where gamma is the boundary of the first quadrant or a corner. So if gamma looks like this, where this is 0, 0, let's say. So I should say, in this case, this passage time, depending on what g naught is and depending on what gamma is, this could be infinity, right? Because if, for instance, if my gamma was flat, let's say it was the x-axis, right? Then there's an infinite number of paths, right? The paths could kind of go back arbitrarily far. And so unless my g naught has some sufficient decay at minus infinity, I'll be taking a max of more and more random variables. Let's say g naught was 0. Then I could just kind of go arbitrarily far, add up an arbitrary number of geometrics, and I would diverge. So as long as our paths are kind of infinite in both the minus 1, 1 and the plus 1, minus 1 direction, then we're OK. And the kind of the extreme case is where gamma is a corner. And so in this case, and let's also imagine that g naught is identically 0. So if that was the case, then all paths really you can think of as leaving from 0, 0 and going, say, to x, y. And we can define gxy in this case to be the max over all paths, or maybe I put 1, 1 in the notes. I don't think it matters. All right, so sometimes you'll see this referred to as the corner growth model. This is sometimes called the corner growth model. Where you restrict yourself to an initial data, which is a corner, with 0 initial data, or initial boundary, which is a corner, and g naught being identically 0. So in that case, the max is over all paths. Well, it's over all paths from the boundary, but you might as well take it the starting points to be 0, 0, because there's no reason to restrict yourself away from that. You can see now that the gxy, this is of course true in the more general setting I gave you over here, but let me just state it here, satisfies a simple recursion relation, which is that if I want to know the value here, let's say that you wanted to actually compute this, on a computer, right? You could maximize over, the 2 to the whatever many paths and solve it that way, but that would be a really bad way of doing this. The better way of computing these gxy's is through a recursion relation, which is to say that the maximum to get to here is I need to go either through this point or this point, and then I have an additional weight. So it's the maximum of gx minus 1y, gxy minus 1, plus the weight at xy. Okay, with the initial data that it's 0 on this left and bottom. Okay, so this recursion relation is very simple, and from it you can in fact see that this gxy is somehow recording the times of growth of a model. And so let me just define what that is. So let's define AT to be the set of all xy in this quadrant such that gxy is less than or equal to t. So A0 is the set of all points that are less than or equal to 0. So A0 is just this boundary. So this is A0. And now as t progresses, right, think of just t as like a time, a time that's progressing forward. Occasionally, you'll see a new point that occurs in this set. And the time it takes for a new point to occur in this set, well, the dynamics will be the following. So once you have 2 points, say x minus, so if this is point xy, once you have the point x minus 1y and xy minus 1, once both of these are in the set, the amount of time it takes until the next point is in it is a geometric random variable with mean q. Okay, so that follows directly from this recursion relation. And so in other words, the dynamics of this AT are Markovian because, of course, the G's are memory, the W's are memoryless. These are geometrics. And the dynamic is simply that once you've added points in, you wait a geometric q amount of time and then add in the new point to the right. Now, of course, because we're in discrete time, these geometrics can be 0. So you can actually add in multiple, you can kind of add in chunks at a time, right? Because it might actually take you 0 amount of time to add that in. And then it might take 0 amount of time to add in its neighbors and so on and so forth. So if you're uncomfortable with that, you could always change the definition and have the W's be, start at 1. But anyway, that's just a deterministic shift. So this happens after time geometric q. So the time increment. Okay, so after some amount of time, you would, you'll have some sort of profile. So let's say AT. And again, the type of question that we're after, or that people are after, is to understand what does this profile look like as a function of time. So now you run this growth process for a very long period of time, and you say, well, what is, is it random? Is it somehow deterministic on a certain scale? What shape is it taking? And it turns out that, in fact, it takes kind of a rotated by 45-degree angle parabola. So if I were to rotate the picture by 45 degrees, what will happen is there's a sort of a finite speed of propagation on the two axes. This is pretty easy to see because I always have the bottom point. So the time it takes for this sort of bottom thing to progress is just the sum of geometrics. Or, in other words, gx 0 is just the sum of the geometrics because the max term is kind of an easy one. And so there's a certain speed which is determined just by the geometric parameter q. And then this shape. Sorry, I said it was a parabola. That's true in the exponential case. In the geometric case, it's a more complicated curve, but I'm not going to write it down. So anyway, so there's some law of large numbers, and then you can ask about fluctuations. And so we'll get to this in the fourth lecture. We'll prove results of this flavor. Okay. Just another note is that there is yet another interpretation. So here is a growth model, this corner growth model. If you kind of look at the picture and rotated it by 45 degrees, you see this interface is just composed of kind of plus and minus 1 increments. And if you think of plus and minus 1 increments as actually particles and holes, then this gives you an interacting particle system, a discrete time interacting particle system where you have a dynamic whereby a particle and followed by a hole can turn into a hole followed by a particle. You understand? When you do this change, so if I rotated my picture, so I think of this as like a particle and this as like a hole, then after some amount of time, I add in this block, and now the two have swapped. And so this becomes some discrete time interacting particle system. And if you've ever heard of the totally asymmetric simple exclusion process, this is some version of that. Okay, so I'm not going to dwell on this. It's just a side remark. And I'm going to really focus primarily on this setup of last passage percolation. So any questions before I kind of start to do something with the model? Is the model clear? And definitions clear? Okay. If at any point it becomes unclear, let me know. Okay. So what I'm going to focus on in this first lecture is the stationary measures. And as you know from Markov processes, stationary measures are very valuable. Okay, they tell you about long time limits, but in fact, in this context and in the context of interacting particle systems, stationary measures can tell you a lot about non-equilibrium behavior, non-stationary behavior, because somehow they let you approximate the dynamics in some scales. Okay. But what the heck does stationary measure mean for this model? Right? Because if you think about it, once I've specified let me imagine I specify, some initial profile, as gamma and some initial data, and I start to run my process, right? I build my G's, so I have my G naught defined along here, and now I get my G, P inside of here. The G's I get by doing this variational problem and adding a bunch of geometric random variables. So in absolutely no sense will the G be itself stationary, because as I move further and further out, it will necessarily get bigger and bigger, right? Because I'm taking more geometric random variables. So the G themselves will not be stationary. So that's not the notion of stationarity that's relevant. The notion of stationarity that's relevant is somehow related to the notion, this side remark I mentioned, that the derivative of the interface is an interacting particle system. And so what I really will care more about is increments and stationarity of increments. And that will be what's relevant. So let me define what I mean. So we're going to so we fixed our initial profile, our downright path gamma, okay, and we fixed some initial data G naught, and from that I'm going to define a collection of random variables, UI naught and VI naught. And what these U's and V's will so it's I and Z. These will correspond to increments. So these will be horizontal. So these are horizontal and vertical increments of the initial data. So maybe a picture is better than trying to write out a particular definition. So here's my picture, and somewhere I decide that I'm going to start with G0 minus 1 in the other direction. So let me draw this a little bigger. Okay, so I have maybe this is what my path looks like. So I'll call this increment. So my initial data G naught specifies some values along this path. So maybe I have the value 4 here, 2 here, I don't know, 1, 3, I don't know, minus 1, 0, so on and so forth. And so I need to, I can choose where I start my increment numbering. So maybe I call this one U0 naught, and this one will become then U minus 1 naught. This increment will be U1 naught. I suppose this I should call U v naught, v naught sub 0, and this one will be v naught sub 1, and this will be v naught sub minus 1, and so on and so forth. Okay, so I've just labeled them, and of course I should tell you what their values are. So the u increments, I always take the value to the left minus the value to the right. So this u naught 0 would be equal to 0 minus 4. So in other words, minus 4. Okay. And for the v's, so v naught 0, I take the value on the top minus the value below it. So this would be 4 minus 2. So this would be 2. So I'm always, I kind of imagine I'm traversing from this direction down. So I'm always taking the first point minus the second point. Okay, and so 0 to 4, so a minus 4 increment, and this 4 to 2, this is a plus 2 increment. Okay, so I'm just kind of reading off the differences along here. And you see, of course, that these differences don't matter. If I added 1,000,000 to everything, I'd have the same differences. So this is already a good thing, because that's going to help us towards getting some notion of stationarity. Okay. So these numbers are specified by the initial data up to a shift of the initial data. So, I could shift every value in the initial data up, and it wouldn't change them. Now, the notion of stationarity that's kind of most useful for me is that I'm going to imagine taking my gamma and shifting it. Okay, so remember, gamma k was equal to gamma plus kk. So it was this shift in the 1, 1 direction by k increments.
Sorry?
Yep.
In your notes, you take the opposite convention. You have x minus y.
Oh, you're right. Yeah. Oh, good. Okay. So then forget what I said about taking things. That's right. Okay. Yeah, and this is the right convention. Sorry. The reason why I take the opposite conventions is the following. So the convention that is in the notes, which is actually the correct one, is that in both cases I take whatever value is here and then I subtract either the value to its left or below. Okay, so that's the convention. And the reason is that you should always expect the value here to be bigger than the values at these two places. At least once you've moved into the bulk, this will be true. Right? Because the value here, by this recursion, is the max of the two values plus something. Okay? So that's kind of the right notion. These increments, at least once I've moved in, will always be positive or non-negative. All right, thank you. Thanks. So with that corrected convention, I can define the UK i's and VK i's, which are the increments of the G process. So these are the horizontal and vertical increments of G along this shifted gamma k. So what do I mean by this? So I've taken my shift, let's say I do gamma 1, so I just shift every point to the right by 1, 1. Okay, so this is my new gamma 1, gamma plus 1. And I get my G values by doing the definition. So either I use my recursion relation with this as the initial data, or I just take the max over all paths, that go from here back to the initial, back to this boundary. And okay, and I get my bulk field of G's, right? So I define the G's inside of to the upright of my initial path. And then I look at the increments along G. So now I would have that, I guess this would be U1 minus 1 would be the corresponding increment. Right? So I've shifted everything up by that. So this turns into this. And, oh no, sorry, this one becomes that. So this is u1 minus 1, is this increment. Okay. So now these start to depend on the bulk weights. Okay. So is that clear how I've defined these ui's and vi with the super k? Okay. And now the definition is that my initial data g naught on gamma in the set of downright paths is called stationary if the joint law of uik vik for I in Z is independent of the value of k bigger than or equal to 0. So in other words, if I were, let's say I chose my initial data g naught just to be identically 0. Okay, so identically 0. Clearly that is not stationary because once I move into the bulk, that would require that my g's are identically equal along the downright path shift, which would really mean that it's just identically, it's some deterministic object. But that's not true. That's just clearly not true. So g, not being identically 0 is not stationary. And I can demonstrate lots of other examples that are not stationary. But the question is, what is stationary? And so this is at least the definition of what it means to be stationary. Is the definition clear? Okay. So now, of course, once you know the stationary measure on a given downright path, do you really need to do this for every downright path, right? That's seems like it would be a bit of a bother, right? And the answer is no. Somehow, let's say that I can demonstrate to you a stationary measure on a given downright path. Then what you can do from that and the stationarity is the following. So you imagine actually shifting the initial path in the minus infinity direction. So shift it by minus k. So as I do that, if I'm only interested in these increments, the law of the increments that I see in the bulk doesn't change by stationarity. And so I can actually take my initial data, my initial path, all the way back to minus infinity, minus infinity. And what I'll see in here will just converge to a stationary measure on the infinite plane, on the entire plane, on the increments, right? And then I can choose any downright path, and what I see along that, the increments will be stationary just by the stationarity of the whole field. Okay, so from any downright path, I can actually access the stationary measure on any other downright path. That doesn't mean a priori that knowing it on one path gives me a nice formula for it on another path. But we'll see in just a little while actually that on any downright path, the stationary measures are actually very simple and very nice. And this is a useful thing. And in fact, a very useful perspective is to ask the question, which is kind of more of a local question, which is if I know the stationary measure on a given downright path, how do I get the stationary measure on a path where I've just modified it locally by, say, flipping a corner into an upper corner, lower corner into upper? So what is some sort of local consistency that I'd like of the stationary measure, and how does that then give us the structure of the stationary measure? Okay. Now, of course, there's a very nice question, which is to characterize all stationary measures for this model. And it turns out, I won't prove this, but it turns out that there's a one-parameter family. I'll give you what they are, but I'm not going to prove that it's just this. There's a one-parameter family of stationary measures for this model. how should you think of these is the following. So, imagine that I took my corner growth model, right? This situation with 0. And imagine that I took this starting point and I pulled it away to infinity, but in some direction, right? So I chose some direction in this fourth or whatever, in the third quadrant, and I pulled my starting point backwards in that direction to infinity. Now, when I do that, I can look at the increment process still, in the bulk. And the claim is that will converge to a stationary measure, but the choice of stationary measure will depend on the direction in which I pulled the point. And so for each potential direction, there will be a stationary measure, and that will constitute all stationary measures. Now, again, that's something you need to prove. What I'm going to do is something somehow simpler. I'm just going to tell you what the stationary measures are and give you an exercise I'll tell you how to do to prove that it is in fact stationary. Proving these sort of statements of convergence, really the sort of ergodicity, the domain of convergence of these stationary measures is a harder task. If you specify your favorite downright path and your favorite initial data, and then you ask me, well, at infinity, which of these stationary measures will occur, it's not so hard to guess what it is, but to prove it will take a little bit of work. Okay, so let me tell you, now that I've hopefully built this up, what are these stationary measures? And then I'll tell you, without much detail, how, for instance, you could use them. And this is where I think the first mistake is. What I wrote about the shape theorem, I think, was just bullshit. Anyway, I'll try to remedy that. So let me give you the one-parameter family of stationary measures. And I'll parameterize this one-parameter family by 2 parameters. Something seems weird there. Let me assume that A times B is equal to Q. Okay, so it is one parameter. Once I've specified A, you know what B is. But it's helpful to just write it in this way. So I have any 2 positive reals that our product is Q. Okay. Obviously, just one of them matters. And any downright path gamma. Okay. Then, given that, let me define my initial data with the property that the horizontal increments are geometric with parameter A, and the vertical increments are geometric with parameter B, and everything is independent. All are independent. So what do I mean? So, you choose your favorite downright path, and then I'm going to choose increments along it. So the horizontals are always increment geometric A, and the verticals are always incremented with geometric B. Okay. So then the theorem, and I'll call this theorem 1, is that this law is stationary. Okay, in the sense here that if I wrote this in terms of G naught, but in the sense that if I now write down the corresponding G naught, of course I need to specify some absolute shift, but that doesn't really matter because I'm only looking at increments. That the increments that I get by kind of progressing in the 1-1 direction will have the exact same law. And actually, a much stronger result is true, and this is going to give you the tool to prove this, which is the following. So here's the sketch of a proof, and you see in the notes there's an exercise which is to actually prove this. That in order to prove stationarity, it suffices to prove a local property, which is the following. So if I have 2 random variables, u and v, okay, where I guess the pair uv is jointly given by an independent set of geometric A and geometric B. So exactly what you would have locally in this under the stationary measure. Okay, so now there is a transformation which is given just by the LPP recursion, and I'll write it down for you, which gives me U prime V prime, and it involves knowing a weight, a random variable W that's distributed geometric Q. Okay. So, what am I doing? I'm saying I know this increment, I know this increment. How do I get these two increments? Well, I need an additional independent geometric Q, and then I just use the definition to write down what this U prime V prime is. And if you do that, and I'll let you check this, you have that U prime is equal to the max of U minus V and 0 plus that omega, or W, whatever. And V prime is equal to the max of V minus U and 0 plus omega. So in other words, a very simple recursion on the increments plus this common geometric. And so the claim is that if I have this as the initial law, then U prime V prime also is distributed as this pair of independent geometric A, geometric B, random variables. Okay, so this is a very local statement. It just says that the LPP recursion locally preserves the property of this stationary measure. So this is a local preservation, and so once you prove this, then you can basically just iterate, you do this local operation where you just locally transform each of these. You transform to the new path gamma plus 1, and you've changed it in a way that you have the exact same stationary measure. Okay. I want to make a small point, which I'm not going to use really, but which is that the stationary measure has this independence property along the given downright path. But if I look kind of simultaneously at the law along this path and the law along this path jointly, they are not independent of each other. Okay, so just if I look marginally along a single downright path, do I have this nice independence property? It would be too easy otherwise. Anyway, so the exercise is to prove theorem 1. Now, theorem 1 is really the first instance of a Gibbs measure describing a stationary measure. Now, how is this a Gibbs measure? This is such a simple object. But if you think about what this law is I have a configuration space, right, which is given by, well, whatever the values, the potential values are on these vertices, right? And the law is given by the product of Boltzmann weights, which are of the form Q to the increments, the differences along edges. So for each edge, I have a weight, which is Q to the increment. I take a product of this, and I get a weight for the entire configuration. Of course, this is not normalizable. This is an infinite thing. But anyway, you can still make sense of this, in the same way that you make sense of an infinite product measure. So this is a Gibbs measure, a very simple one. All right, questions about the result? Let me check that. Yep.
In the recent figure you draw, there is omega at the up right corner.
Yes.
And can we define kind of omega prime in the bottom left corner of the second?
I see. In some way that it kind of preserves the property of the triple. Yeah. There is. I don't have it off the top of my mind. Well, okay. I guess it would just be there's some transformation that gives you an additional random variable here, which actually preserves the triple independence. Yeah, I need to think for a moment about the correct way to define the omega prime here. But you can do this, and in fact, if you do this properly, then you actually end up producing some sort of reversible picture, right? Where you have your pairs and you have your omegas, and as you kind of trace through, you have these other omegas, and you have these, you have these omega primes, and you have a picture in the opposite direction. Okay, but I don't have this uploaded in my head right now, so I'm not going to venture to say what that is. So, yep.
It's not really reversible because the B's and Q's switch.
Yeah, what I mean is that somehow if you're going to look at the picture, if you do this transformation and you look at the picture now from this direction, there is some kind of similar picture that you can do looking in the other direction. This is not a reversible dynamic, though. No, it's somehow, okay, I need to take a little while to think about it, but okay. Let me not dwell on that. So let me mention just an application of knowing this stationary measure. And I think what I wrote in the notes is probably bullshit. I need to spend a little bit more time thinking about it, but okay. But let me talk about for a moment how you can use this, say, to compute the point, at least the asymptotics of the point-to-point last passage time. So, you see, what does this stationarity picture give us? Well, it tells us that if you choose your favorite path. So, for instance, if we chose the corner growth model, it would tell us that if we have geometric B and then geometric A variables along this, that this is a stationary boundary condition. And in fact, it will tell us more. This proof will tell us that if I start with this as my initial data, and I start to run LPP, this recursion relation I just erased, and I kind of look on some more general path now, that along here I'll have the same sort of increment process. Okay? So this is a very nice picture. In particular, maybe another way of thinking about this is the following. So let me take a point which is far out, so x, y, and I'm imagining this is going to infinity, with some fixed ratio between x and y. And I'd like to compute the last passage time without these boundary conditions, but just the sort of, what I had called gxy. So the point to point, imagining that these were actually 0 and 0. Okay? But a priori, what I can do is I can actually compute the expected value under the stationary measure. So if I look under the stationary measure, so maybe I'll call it under the AB stationary measure, I can compute the passage time, but with respect to this initial data, right? That's a very easy calculation because all I need to do is actually change my downright path to look like this, and now I can compute the, so now I know that this increment process from here to here is just a sum of a bunch of IID geometrics. And moreover, I know kind of what, at least an expectation value, I know that this is also a sum of geometrics. And so I get that the expected value here is the difference of this sum of geometrics and this sum of geometrics. Of course, these are correlated sums of geometrics because this is not along a downright path. But I'm taking expected value, so I don't care about that correlation. Okay? So I can very easily compute this expectation in terms of kind of knowing, well, it's going to be something like, x times the expected value of the horizontal increment, which is geometric A, minus y times the expected value of the vertical, which is geometric B. I think this is correct, I believe. Okay, so great, but now you see, when I do this, how is this expectation actually being achieved? Right? There are paths that are kind of going backwards, these paths pi, and eventually sampling a boundary data point, right? And you see now, as I tune the value of A and B, again, respecting their product being Q, the trajectory that this path takes, it might favor, so if B is getting bigger and bigger, it might favor going to this boundary because I have bigger values along here. Or if A is getting bigger and bigger, it might favor going here. So as I transition my values of A and B, there's of course a range in which they can live. As I transition basically from having A close to 0 to having B close to 0, the maximization point is going to move, at least at a law of large numbers scale, and transition all the way around from one corner to the other corner. Now the true last passage time, so the last passage time without any boundary condition, so let me kind of imagine putting 0 boundary condition in, will be achieved somewhere for some value of A and B. At least, at the law of large numbers, this seems plausible, that there is going to be some value of A and B for which the maximizing path actually crosses through this point and doesn't really use the boundary information at all. And so I should be able to achieve this by minimizing overall A and B, such that the product is equal to Q of this quantity. Because after all, the last passage time from this point to this point without using the boundaries is always going to be smaller than the last passage time using the boundaries. And I claim that there will be some value of A and B for which I effectively don't use the boundary. And so that's why this minimization will occur. So, okay, of course, it will take some work to turn this into a statement that actually proves that this is the law of large numbers and so on. But this will give you a formula for the law of large numbers for the point-to-point with 0 boundary condition. Okay, and this is, very nice. It doesn't directly give you information about higher moments, fluctuations, things of this sort, but there are techniques that have been developed that actually use the structure of the stationary measures to build up all sorts of information. You can compute the fluctuations of the point-to-point passage time. You can compute the tails and things of that sort. Okay, so that's not the direction I'm going to take these lectures, though. But I just wanted to kind of motivate that these stationary measures are actually very powerful. Okay. Questions? So I've been speaking now about the LPP on the whole plane, but what I want to focus really on for the rest of this and the next lecture is LPP on a strip. Before doing that, let me mention, you may have seen this related model of TASAP or ASAP, exclusion process on a strip. And the model there looks like the following. So imagine that you have, this is an aside, so imagine that you have a sort of reservoir and then a finite number of lattice path points, so 1 through n. And you can have particles with at most 1 particle per site. So this is something called open ASAP. I'll describe for a second, which says the following. So there's a certain rate at which particles get pushed into the system or removed from the system. It's usually denoted as alpha, beta, gamma, delta. And then there's an asymmetry that particles jump left or right with some rate, I don't know, q and 1. So this is a continuous time process where basically particles get fed or removed from the boundary at certain rates, continuous time, and then they jump within, subject to the rule that they can't jump on top of each other. And they do this in continuous time as well. So this is a very well-studied object. It's a finite dimensional continuous time Markov process. And for the last 30 or so years, people have been very interested in studying its stationary measure or stationary measures of similar models. And the boundary conditions induce very interesting behavior. In particular, if you looked at this model with a periodic boundary condition or on the infinite setting, product Bernoulli would be stationary. Okay, so this is a well-known old result. But when you introduce these boundary conditions, you generically break the product Bernoulli structure, and the stationary measures become considerably more complicated and have typically required a technique called matrix product ansatz that was really spearheaded by Bernard Derrida in order to study. Okay. So I'm going to define a model which is somehow a last passage version of this, and talk about the structure of its stationary measures. And the structure actually avoids direct use of this matrix product ansatz. So somehow the innovation that I want to describe is a technique that doesn't require the notions of matrix product ansatz. If I have time at the end of the next lecture, I'll actually come back and explain how what I'm describing actually can be thought of in this lens of matrix product ansatz, but it becomes, something that you a priori might not have understood or solved through this technique. So that's, okay, a little bit of side note, background. Let me describe the model and the results. And that will probably bring me to the end of this lecture. So I'm going to fix a strip that will have some width n. And now you'll see my strip drawing skills are pretty basic. But imagine that I have, so this I think of as 0, 0, and I have something that goes up to n comma 0, I guess. Okay, so n in this case, 1, 2, 3, 4, 5, 6. N is 6 here. Okay. And then I have lattice points. And so the slope of the strip is supposed to be 1. Obviously, the picture might not make it look as such. But hopefully this is clear from my words. Okay, and so on and so forth. I'm going to call this the left boundary, and this the right boundary. Nothing complicated there, and I'll call this the bulk. So already you see, in comparison to this ASAP model, there's a diagonal shift. Of course, you need a diagonal shift here because the recursion is kind of always pushing in the diagonal direction. But this is very much analogous, though. Now I need to define weights for my model, and I'll define the weights in such a way that they will depend on whether I'm at the left, the right, or the boundary, or the bulk. So the weights, they'll all be independent, and they will depend on some parameters. So this will depend on the parameter A, CL, and CR. And these will all be assumed to be positive with the property that A squared, A times CL, and A times CR are in the interval 0, 1. Okay, these conditions will be obvious why they're important in a moment. So the weights are all geometric, and the parameters on the left are A times CL. The parameter on the bulk is A times A, so A squared. And the parameter on the right is A times CR. Okay. So in other words, I have my, this one is geometric with parameter A times CL. This one A times A squared, and this one geometric A times CR. Okay. Then I have some initial data. I'll call again G naught, and I'll normalize it so that G naught at 0 is equal to 0. Okay, so I'm going to set this to be 0. I'm going to just call it G naught 1, G naught 2. So I'm going to take my initial downright path to be horizontal here. I could have done it more generally, but this will be simpler, all the way up to G naught of n. So this is my initial data. I specify some initial set G naught along the bottom of the picture. I specify weights in the bulk of the picture. And now I can define exactly as before the last passage time. So I could have defined it through the max overall downright path from a point to the initial data of the sum of the paths, plus the initial data, or equivalently, as I'll write it right here, just in terms of the recursion relation. So let's define gxy, which for any point above this level 0, through the recursion relation that this is equal to omega xy plus, maybe I'll clear a little more. All right, if I'm in the bulk, it's the usual thing. I take the max of, sorry, that should be capital, gx minus 1y, gxy minus 1, if I'm in the bulk. If I'm at the left boundary, so the last passage time to this point will just be equal to the w at the boundary plus the value directly below it, and similar on the right. So this is gxy minus 1, and this is gx minus 1y. Okay, so this is, again, saying that if I want to know the value here, I could have defined the gxy's as the max over all downright paths that sample the initial data at one point of the sum of the weights along the path. So if my x was here, I have some downright path, and then I take and I eat up my g naught somewhere. Of course, that's kind of an inefficient way of computing it. I better do it through the recursion, and the only thing is that the recursion says at the boundary, I'm kind of forced to go back into the bulk. So I can only use the one term from the bulk. Okay, and of course, there's the initialization that g x comma 0 is equal to my g naught of x. Okay, so this defines my LPP on a strip. Is that clear, definition? Now you see this is similar. You have these bulk effects, these CL and the CR, and somehow the choice of the CL and the CR should be changing the nature of the stationary measure. But of course, I again need to tell you what stationarity means, but it should be somehow obvious. Stationarity really means that the increment process should be stationary. Now again, I could do this for an arbitrary downright path. I could talk about initial data on an arbitrary downright path. That would be fine. Let me focus, just for simplicity, on the horizontal path, in which case the notion of stationarity is the same as before, but let me just write it out to be concrete. So my g naught is stationary for the horizontal path, or gamma horizontal, if the law of the increments process, and actually I can write it in a slightly different form because I have a rightmost particle, so I can write it as k plus ik minus kk, gkk. So I'm basically looking up at height k, and I say, well, this is gkk, and I ask about the value of every point along this horizontal path, how it differs from the value of gkk. And that the law of this for I equals 0 to n should be is k independent, so is independent of k bigger than or equal to 0. Okay, so I want an initial data which has the property that whatever it was, the increment process on the bottom is maintained as I move up vertically. Okay. So you might hope that that this is also going to be product Bernoulli, or the way I've written it, product geometric, or the way that I've written it, that this would be like a random walk, like a geometric increment random walk, right? Because I've normalized by the rightmost value. So you might hope, okay, that each one of these increments should be like product Bernoulli, product geometric. And that would be great, right? But it's just not going to be true. You can easily convince yourself through examples that that is not stationary, or at least not generically stationary. There'll be a very special case where it will be. So let me give you a result. So the theorem says that the stationary measure, although it's not itself a product measure, is somehow an object with just one extra layer of complexity. So it's going to be the marginal of a two-dimensional process described by a nice Gibbs measure. So here's theorem, what I'll call theorem 2. So we're going to, fix our setup, fix our A's and C's, okay? And let's see. Well, first of all, it's pretty easy to convince yourself that for fixed values of A, C, L, and CR, there will be a unique stationary measure. Okay? But this uniqueness is because it's going to be somehow, it's not finite dimensional, but it's somehow compact in some sense. And so, or in other words, if I choose any sort of initial data, there's a positive probability on the increments of getting to some other increment values after one step or a few steps. So that alone is enough to show that the thing is that there's a unique stationary measure, moreover to show ergodicity. Okay, so this is part of the theorem, but this is kind of easy part. Okay, so there is a unique stationary measure, but let's see, the unique ergodic stationary measure. I don't know why I used lowercase g versus uppercase. Well, okay, anyway, I'll stick with lowercase for the moment. But the unique stationary measure g naught, unique stationary g naught, and I've specified g naught to be 0 at 0, which is why it's unique. Has that the law of g naught is equal to the law of something that I'll call L1. Okay, I haven't told you anything yet. What is L1? So where L1 is going to be the marginal of a measure that's supported on L1 and L2. So, so where, let me define first L1, or maybe Li for I equals 1 and 2, is a set of numbers, Li 0 up to Li n. Okay, so you should think of this as two sets of numbers. There's L1 and then there's L2. The dimension of L1, the number of things in L1 is the same as G. I need to specify that L1 and actually L2 both start off at 0. And the law of the pair L1, L2 is equal to a normalizing constant that will, of course, depend on A, CL, and CR. I'm not going to write it down, times the following thing. So there is going to be a Radon-Nikodym derivative factor, and then there's going to be a measure I'll call PGO, L1, L2. Okay, so I'll tell you what this is in a moment, but let me tell you what the Radon-Nikodym factor is. So CL/CR raised to the maximum, j equals 1 to n, of the difference of L2j minus L1j minus 1. And then CR raised to the L1n minus L2n. And then this PGO measure, where this is the law of independent L1 for L1 and L2, geometric A increment random walks. Okay, that's the theorem. Let me spend a little bit of time parsing it. So this object here, PGO, this is the thing that you would kind of imagine based on my earlier discussion about the model in the infinite volume, right? When you're in the infinite volume and you look at a horizontal path, the stationary measure was just, the increment was just a sum of geometric A, or I guess geometric A random variables, right? That was the convention I used. So here, my underlying measure is the sum of geometric A random variables. It's just that now my L's represent partial sums, right? So I have L1, which has that law, and then independently L2 has the same law. L2, it's not clear what the meaning is going to be from this picture. But anyway, so I have my L1 and my L2. But then I'm going to pervert this measure. I'm going to reweight it by a factor that depends, well, this factor is kind of easy. It depends just on the relative distance between L1n and L2n. So I have my two random walks. They both start off at 0. Obviously, they're OK. I'm going to draw them like Brownian motions, but obviously these are geometric jump random walks. But so they both start off at 0, and then I reweight it depending on if CR is bigger or less than 1 by kind of the difference at time n between the two. So there's this sort of linear potential that's being applied. If I think of this as e to the something, there's a potential which is linear in the difference at the right endpoint. But then I have this functional that depends on the entire trajectory. And I'm looking at this sort of running max of the difference between the second curve at time j and the first curve at j minus 1. The increment matters, but kind of, at least heuristically, doesn't matter that much. I'm more or less looking at the maximal difference between the two curves over the entire trajectory. And I'm, again, reweighting by some exponential factor depending on that. Now, when I do this, no longer do I have a probability measure, and so I need to normalize. And so the theorem, first of all, says that this normalization is finite. In other words, I can renormalize to get a probability measure. And of course, when I do that, I've mixed up, the two measures are now related. Initially they were independent, but of course the Rotter-Nikodym derivative intertwines them. And so I have L1 and L2 now some correlated objects. And I look at the marginal on the first curve, and that's the stationary measure. That's the result. So an exercise in the notes first is to prove that this normalization is always finite. And the second thing is, well, here's an observation. Imagine that CL and CR, the product equaled 1. This is a very special case. In that case, this is just going to be, this whole thing is equal to 1, right? And then what I have here is geometric reweighted by CR to the difference in the endpoints. But of course, this factorizes. And so what I really have is geometric where L1 becomes geometric with parameter A times CR, and L2 with A over CR. And so from this, you see that in the very special case where CL/CR equals 1, L1 is itself a sum of Bernoulli, or so a sum of geometrics, independent geometrics, with this parameter A times CL. So that's a special case that's like tuning the boundary conditions in exactly the correct way. But besides that, this is not going to be product. Anyway, so the exercise asks you to prove that when CL times CR is equal to 1, that you do have product geometric, and to do that without using this formula. Okay, so that's what an exercise is. So, okay. So I think I end in 3 minutes. So what I want to do next, and I'm not going to do it, I'll wait till the next lecture, but is let me kind of tell you, we're going to prove this theorem, okay, so don't worry. Let me give you the sort of outline of how we're going to approach this theorem. Okay? So what we're actually going to do is we're going to start in the next lecture this afternoon with a theorem 3. Okay? And what theorem 3 will be is it'll be another version of writing down the stationary measure. But it will be written in a somehow a more local way, right? You see that this depends on some running maximum. This is a slightly complicated object. So I'll write, in a sense, a simpler formula, something that will look like a Gibbs measure. It will be a Gibbs measure. So I'm going to write what we'll call a two-layer Gibbs measure formula. Now, once I've written down that two-layer Gibbs measure, the proof that it is stationary will somehow be in the spirit of this proof that we gave back for the model in the full space, right? There's this preservation of some local Gibbs weight structure, right? You know, before it was this uv goes to u prime v prime preservation. Here it will be slightly more complicated because we'll have this two-layer Gibbs measure, but nevertheless there'll be some local preservation of the structure of the Gibbs measure that will give us stationarity. That will be the proof of theorem 3, but theorem 3 will have a restriction, which is that CL times CR actually will be forced to be strictly less than 1 in order for this to make any sense. This is required so that the measures in theorem 3 can be normalized. And then to get from theorem 3 to theorem 2, you can achieve this through a rewriting, some sort of integrating out of the formula from theorem 3 that will give me this formula. The two formulas will match as long as I have this restriction, CL and CR product less than 1, and then I can use some analytic continuation argument to actually show that the stationary measure is analytic in the boundary conditions. This is analytic in the boundary conditions. This thing I didn't have defined, but anyway, the equality is on an open set, and so it will be sufficient for proving this theorem 2. So really, the guts will come to theorem 3, and theorem 3 is where the structure is going to be more obvious of these stationary measures. And in particular, what we will see in theorem 3 is that the structure of the stationary measures depends really on two things, something called a Cauchy identity and something called a Littlewood identity. And these are going to be very simple examples of the more general Cauchy and Littlewood identities, but and these are not going to be hard things to prove or anything like that. But these structural properties will give rise to these Gibbs measures and the preservation of the model and everything. And these are things that can be generalized in considerable directions. And so in the later lectures, the third lecture and so on, we'll kind of continue to build primarily off of the Cauchy. This has to do with the bulk dynamics and understand how you go from two-layer to arbitrary layer Gibbs measures and the relation to models like LPP and things of this sort. Okay, so let me stop here. If there are more questions, I can also field them, but I know we also have a photograph to take.